Okay, we'll work through homework problem 526. This is the one with the outrigger on the crane, as well as we have, we'll use Excel to plot the values of theta until we achieve tipping. So when we're looking at this, what do we have going on? We have a couple of masses. So G1 is going to be pulling down there, G2 is here kind of in the middle of the boom pulling down, and then last we have our load here that's pulling straight down over as well. Those are countered by reaction forces at A and B. And there's actually another set of these outriggers on the back side of this crane truck as well. So we have a number of things here. We're told that the mass of the crane and truck is 18 megagrams, and the center of mass is at G1, so that's the load that's here. That's 18 megagrams. And then at the boom has a mass of 1.8 megagrams. So G2 equals 1.8 megagrams. And then finally our load is 1.2 megagrams. This is 1.2 megagrams. And that M looks a little bit like a mu. Excuse me about that. Let me see if I can fix that. There we go. Alright, so what is the approach here? Well, first thing, we'll write some equilibrium equations. So the sum of the forces in X have to be 0. Is there anything in X? No, so that's that doesn't help us. We also have some of the forces in Y have to be 0. Does that help us out? Certainly. So we have that goes to, we have the reaction at A, I'm just going to say normal at A plus normal at B. Those are going up, right? So we have these reaction forces. The ground is pushing up at those points on the outriggers, which is supporting the crane. So that equals, so then we're also going to subtract off the 18 megagrams times our 9.81 meters per second squared to get a force, minus 1.8 megagrams times 9.81, and then 1.2 megagrams times 9.81. So that's what we have. We can rearrange that, but then the last part, when we don't have any tipping, some of the moments around B is going to be 0. So what is creating moments around B? We have the normal force at A, and how far away from B is that? Well, we've got 2 meters plus 1 meter plus 1 meter, so 4 meters. We're going to have that times 4 meters. And that's actually a negative, right? That's creating a clockwise rotation, so that's a negative moment. And then we're going to have our load at G1. I'm just going to call it G1. It's actually going to be that 18 megagrams times gravity. G1 times 1 meter. So that's acting here. We're looking just at this moment arm. So that one's pretty straightforward. And then these next ones will depend on our angle theta. So we have this angle theta. We're not sure at what point that's going to be tipping. At some angle of theta, let's say if theta is 0, all the mass is going to be centered on the middle of this boom here. So we certainly won't have any tipping. We will have a positive moment in that case. But then as things start coming out this direction, we'll start getting some, once these centers of gravity cross the point at which B is acting, then they're going to have negative moments. So how are we going to account for that? Well, I'll write them as positive moments, and then we'll see how that works out. So we're going to have plus that force. I'm just going to call it G2 and G1, G3, excuse me, G2. So times its moment. So it's going to be how far from this point to B. We have 1 meter plus 1 meter. So we're going to have 2 meters minus, what's our x displacement here? We're going to have 6 meters times the sine of theta. So when theta is 0, sine of theta is 0, so this part goes away and we have a positive moment. When theta is 90 and this boom is straight out over this way, we're going to have, this could be 1, so we're going to have negative 6 meters plus 2 meters, so 4 meters times that negative, so it's going to be a negative moment. So that's how we'll accomplish keeping track of whether we have a positive or negative moment. Then we'll add, and I'm going to call this G3, so the load up here I'm calling G3. It's kind of a poorly written G. G3 plus G3 times, still have that plus 2 meters, so that's where that center of rotation is happening, where our theta is changing. And now, instead of just 6 meters, we have 6 meters plus 6.25 meters minus 12.25 sine theta. Alright, so that's our moment. Oop, excuse me. Get rid of those. And let's see if I can scroll here. Okay, so we'll continue working through this. So we'll have, if we take our forces here first, so the sum of our forces around y is 0, so we find NA plus NB equals, I'm just going to call them G1 plus G2, G2 plus G3, and we can solve that later. So we'll leave that for now. Expanding this moment equation, we're going to have 4NA, so I'm taking this negative 4NA to the left side, equals G1 plus 2G2 minus 6 sine theta G2. So I expanded this out, so there's my 2G2 that came down to here, and then I have my G2 times my 6 meter sine theta here, which came there, and that's the negative sign came through there. And then we'll have plus 2G3 minus 12.25 sine theta G3. So that's the expansion of this term over here coming down into these two terms. Alright. So if we keep working through that, we'll find our normal reaction at A is going to be G1 plus 2G2 plus 2G3 minus, I'll pull the sine theta out here, 6G2 plus 12.25 G3. So I combined this term and took the sine theta out front here, and so this is plus, so I have the negative sine theta, so this is a plus 6G2 plus 12.25 G3, and that's all going to be over 4. And so as sine theta changes, I can calculate what that normal reaction at A is. And when we have tipping, when NA equals 0 or negative, right? So when NA equals 0, that's when things are perfectly balanced on those B outriggers, and you could walk up to that crane with your hand and pull up on the back and it would tip over, or you could push up on the front and it would put more reaction onto NA. So that's the criteria there. So I'm going to take this equation now and fill that in our Excel model, and then I will also go in here to our Excel and use this equation here to find what our reaction at B is. So I'll use the moments to find A, I'll use our equilibrium around forces in Y to find B, and then I'll report those in Excel. So what do we have here again? We had this giant thing. I've got that written down separately. Let me just scribble it down one more time so I don't mistakenly type it. Plus 2g2 plus 2g3 minus sine theta 6g2 plus 12.25g3, and all those g1s and g2s we have to multiply by gravity to actually find a force in newtons. So I'll just put a small g out front of that. So let me write what I just said there. So I'm going to put a little g here where this is 9.81 meters per second squared. So that gets us an actual force in newtons. And then the other part was NB equals little g times g1 plus g2 plus g3 divided by NA, or subtract NA, excuse me. Alright, so we're going to switch over to Excel now. Okay, we're switched over to Excel here. I've set up my spreadsheet a little bit, so I have my loads in here, and I have my values in megagrams. I can just refer back to those cells then. I could name these if I wanted to get kind of sneaky. I could call this G1. Maybe I won't call it that. I'll call it 1G. That's not going to work. Okay, so I'll leave those the same. I could call this load 1. There we go. I'll call this one load 2. So I'm just typing up here and giving these names. I can refer to those names instead of those values later in formulas. So my angles, I'm going to set those up. I'm going to go 0, 5, 10. At some point I'll see this reaction at A turn negative, and then I'll know I've gone too far and I might need to add a little resolution. I'm going to go up to 90. That will give me enough certainly to get some tipping going on. Let's convert those into radians. So that's going to equal this times 2 times pi. So pi, you have to enter pi and then begin parenthesis, end parenthesis. And I'm going to divide that by 360. So that's 0. That looks right. So when I get up to 90, I should see like 1.57. Perfect. And I could always change my formatting on these cells, right? So I could change it to be a number and say I want to report to 3 decimal places, so it's a little cleaner. And then here we'll start entering our formula. So if you recall, we had our formula that we found in the Word document, and that was this load here is equal to our G, 9.81, and I'm going to divide that by 4 for the denominator, and then I'm going to multiply that whole, excuse me, trying to use my arrows to move around, but I got into trouble there. 9.81 over 4 times, now I've got G1, and I'm going to just use my reference here, load 1 times 1,000, so I had megagrams, so I'm making that into convert kilograms, plus 2 times load 2 times 1,000 plus 2 times load 3 times 1,000. Alright. And then I'm going to subtract off sine of theta in radians times 6 times load 2 plus 12.25 times load 3. And let's see, one more close parenthesis should do it then, right? So I've got my sine there, this quantity in the middle there, and my end parentheses, so that's closing that thing. So that should be my value. looks good. I'll copy that down. Oh, I've got some problem in here. Why is my B10 minus oh, I need to multiply these by 1,000 here. Times 1,000, and then slide over times 1,000. So then let's roll that down, and we should see this changing here. Perfect. So that tells us that our crane is going to tip between 70 and 75 degrees, and probably closer to that 70-degree mark if this is 1500 negative and this is 92 positive. We'll use our other equation to find our B reaction. So this is going to be equals 9.81 times 1,000 times load 1 plus load 2 plus load 3. And we're going to subtract off our value for our load at A. So what do we find there? That seems reasonable. As our crane is tipping over, our load at B is increasing as our load at A is decreasing. And then if we're looking for single reactions, so this was the total reaction at both points, both outriggers at A. So we're going to take that and divide by 2 to find each outrigger's load, and then similarly at B, take that and divide by 2. We can plot that, copy that down. So I'm going to add a little bit more resolution here in this point. So I'm going to insert some cells, and then if I copy these, copy cells and insert copy cells. So now I've got 4, so I should go 71, 72, 73, 74. And then I can just grab all of these, pull those down. And so we see it changes somewhere in the 71 range. I could even insert a couple there. 70.1, 70.2. I'm just guessing at this point. Put one more in there, 70.3. So somewhere between 70.2 and 70.3, almost exactly in the middle there, it tips. Let me put one last in here, 1.25. So this will get us really close to 0, close enough. So there you go. So the total reaction at A there is less than 1 Newton. So you could walk up to the back of that thing and pick up on it, and the whole thing would tip over. Lastly, let's plot this. So I'm just going to copy these values here up to that point, and I can paste them. And there's some special things. I can paste it as values, so that's not going to be an equation. And then if I grab my single reaction there, copy, and I'm just going to paste values there. So now instead of an equation when I click on that cell, I see an actual number. So these will not update if I change something in my equation here, but this makes it pretty nice to create a formula, create a chart. So I'm going to insert a scatter chart. I'll add some lines there. So there we are. Verse theta. So there's my chart. So that's coming down fairly nicely until it gets to 0, and then we end.